Hello everyone and welcome to Module 5 in Fundamental Classification Techniques. Jumping straight in to the overview, this module centers on concepts of essentially ensemble learning. And in particular, we're going to talk about bagging and boosting, two of the more common ensemble techniques that you'll run across. So to start off with, well, what are ensemble methods? And the short answer is it's when you combine together multiple approaches, so more than one, and algorithms to attempt to do better at a particular activity. And that's part of the reason we use them is that ensemble approaches are typically quite good. The two most common ones are bagging, which is around creating additional data by essentially doing a sampling technique with replacement. And then the second is boosting, where basically you adjust the weights based upon how well something did and then train again. And we'll talk more about that in a moment. So jumping straight in this module, you'll have the opportunity to master the concepts of developing analytic models using bagging and boosting techniques. At the end of this experience, hopefully you can explain the concepts of ensemble methods, map data to graphical elements, visualize some data and higher dimensional data, develop classification models using bagging and boosting, and evaluate the performance of those techniques as well. So back to ensemble techniques. So breaking it down, ensemble is whenever you have a group working towards a common goal. Kind of originated, I believe, in the concept of music, where you have a group of musicians working together, and perhaps not that many, but compared to like an orchestra, but it is where things are working together to a common goal, rather than each individual worker or thing doing its own thing. They're trying to achieve a common shared goal. Ensemble learning is whenever you use multiple machine learning techniques together at the same time in some fashion, be it sequentially or in parallel. The motivation is, generally speaking, the more learners, the lower the overall error, because you're able to essentially figure out through the use of a certain algorithm or approach doing well in a certain situation compared to when one maybe doesn't do as well. So the basic rule of thumb, though, more learners, lower error. So an interesting sort of thing. But before we get into that, we need to talk about sampling because it's relevant to bagging. And the basic concepts, as you probably know, but just as a brief refresher, because I'm sure if you're in a data science course, you've probably taken some courses that center on statistics, right? So you've had some stats along the way. And when we talk about sampling, we're talking about a population of items. So in this case, they're numbered from 1 to 9. And whenever you do it without replacement, once something is sampled or taken to be part of a set, it is not returned to that overall population for consideration, which means it will belong in one and only one set. But whenever you do with replacement, once you've retrieved how many ever items you're wanting, 5, 6, 7, so in this case 7, after you've retrieved those 7, they're essentially kind of put back in for consideration. So you've got your 7 that you've sampled with, you sample another 7, and there are going to be some duplicates, as you can see with the red arrow. There's actually more than one. 4 is duplicated as well, so is 5, and so is 2, but or in this case 1 is, so we're pointing at 1. So the basic idea, though, is that you have slightly different sets of data, and that's kind of central to the concept of bagging, is that you are taking one set of data and to some extent artificially creating in subsets of that data using sampling with replacement. So you're putting them back in after you've pulled them out. So moving on to bagging, it's short for bootstrap aggregating. So the idea is that whenever you're doing bagging, you're doing a form of aggregation across with a bootstrap sort of approach. Heard a chirp, so I wanted to see what's going on. I'm guessing that my internet connection is not doing fantastic, which is part of why I'm recording this two ways. So moving back, sorry for the distraction. But bagging is very much about this bootstrap aggregation, and that's a pretty descriptive term for it. It is an ensemble technique that takes your data set and essentially samples it n times with replacement. And within each one of those n samples, they're trained separately on different machine learning models. And then you basically, at the end of each one of them, whenever you're running something through, you essentially vote, right, to figure out if two of the three, so you've got three classifiers that have been trained, two of the three agree, then you go with the two. So you basically vote to determine the outcome. So the idea being the more classifiers you have, potentially the higher granularity of the voting and maybe a better result. But with all things, there's probably a law of diminishing returns. So an example, a little bit of an eye test, but you get the basic idea, the elements of the code. The key piece is in through here, where we're saying we want 3 divisions, and then we have a list of those divisions. And this is doing a resample. In this case, we're pulling out 7 with replacement. And so you're creating a list of these 3 divisions, so 3 sets of 7. Essentially, and creating a list. Then you take that list, and for each one of those lists, you essentially create a classifier. So in this case, a decision tree classifier, and we train it on the item in the list. And then whenever we have the result of that, we put it into a list of learners. And then whenever we're going through and doing some combine and output all the classification using voting, we're going to go through the list of using our list of learners and do essentially a prediction, count the predictions, figure out what the max is, and so on. So basically we're doing the voting and figuring out the results based upon the overall accuracy. So it's an example of bagging in motion. There are, though, simpler ways to do that, and we'll talk about it. That's more of a drilled in version. Moving over to Ada Boost. And this is basically a similar sort of concept. This is around boosting, and in particular we're going to talk about Ada Boost because it's one of the more common ones. And I don't typically like to do quotes, and I try not to read too much to you, but this is a really good one. And it basically, to improve the performance of the model, instead of giving equal weights to all the data in the classifier model, we increase the weights of the incorrectly classified data and run the training again. So that part there is pretty interesting. So you put more weight on the ones that didn't do well, and then you try it again. And then since we have increased the weight of the incorrectly classified data points observations in the next iterations, they have a higher probability of correct classification because the model will give more importance to these data points. So it's basically a way of saying these are more important than the others, primarily because you got them wrong the last time, so focus your attentions on learning this. And so if you think about it, that kind of is intuitively how we do things. So if you are in school and you take a test and you get back the test and you have certain things that you got wrong, and you're given the opportunity to take that test again, what are you going to focus your energies on, right? The ones you got right? No, the ones you got wrong. So it's very much that same sort of concept of improving your results by focusing on the things that were missed. So pretty interesting, and maybe initially you may think counterintuitive, but basically what you're saying is this stuff is what you didn't get right, so focus on it, right? Same thing as if you get a big red X on a question on a test, that's probably where you're going to spend some time, if you get a chance to do it again. An example using the Ada Boost classifier, really straightforward because it is an ensemble method that is so well used and commonly used that it's just, easy to do. And you basically do as we normally do. In this case, we're loading up the iris data set and getting back the labeled and predictions. We're basically having it run through with the number of estimators of 100. And that means it's basically going to make 100 copies of the decision trees based upon the previous weights. So it's going to be getting better each time through. And then it calculates essentially your cross-validation score, which is 94.67. So pretty good result. and really easy to implement, right? Because it is such a common sort of thing. And if you are interested in it, do check out the sklearn Ensemble AdaBoost classifier page that deals with it. It enumerates what the parameters are, what they do, gives you some indication of when you would use them and what you might set for values. Some other boosting algorithms, gradient boost. It's similar to all the other boostings, but it's around how it determines the weights is the best way to say it. So it is gradients is essentially when you're trying to find you're trying to find a minimum or maximum by iteratively going a direction is what it kind of comes down to. So you have gradient descent where you're trying to find the minimum of some value by doing some testing to find values that are less and so on. So you're trying to, it's like you're hiking and you just keep going downhill, right? It's the basic idea. Same thing with, there are the inverse of that. So trying to find the maximum using a gradient technique. So you basically go uphill, hill climbing sometimes it's called. So not too uncommon. An XGBoost, state of the art, and it's a residual gradient boosting technique. So it's a little better than gradient boosting. So the key takeaway here is there's lots of different approaches, and the basic concept of a boost is that you weight the data that you did poorly on internally. The algorithm does it. You don't have to do anything, so that it will do better on the ones that it's missing. Moving over to deliverables, deliverable number 5. So you guessed it, you're to develop analytics models using bagging and boosting techniques. So the basic idea here is that you're working at a cancer research institute. You've been asked to write some Python code that'll predict whether there are some images of some cells are cancerous or not, right? So are they benign or malignant? So your instructions are to use the bagging and boosting classifiers to obtain the results and compare the performance by using the following steps. And these are pretty detailed, so I'll go through them just in case I need to add some color. So load the relevant libraries. That's going to include sklearn, pandas, numpy, sklearn ensemble, sklearn model selection, sklearn tree, sklearn metrics, in addition to the following method, which is the AdaBoost classifier, bagging classifier, kfold, and test train split. Load the CSV data using read CSV into your pandas data frame. Explore the data by basically taking a look at 10 lines using describe to take a look at what's the statistics of the data. And then on the diagnosis column, perform explicit conversion of categorical features to numeric values using the map method. So convert over to from categorical to numeric values using map. Create a test set and training set using the test train split, kind of normal stuff that you would normally do here. So you're basically going to, it doesn't tell you the percentage, so maybe you want to hold out 20% for test. It's up to you. For each classifier, AdaBoost and bagging classifier, create a classifier object, fit the training data into the object, make predictions using the test set, perform cross-validation with 5 folds, so it's telling you exactly how many folds to use in your cross-validation. Record the errors for each cross-validation run and print it out. So basically print out the errors for each one of the runs. What you're to submit is to take that output and then write a short memo to your supervisor that contains a brief description of the algorithm used to perform the computation, so that you can think of this, doesn't necessarily have to be a memo format per se. You could put it into a brief white 1-page or 2-page document, whatever is appropriate to kind of get it outlined. I don't know, since the advent of email, how many memos get written, right? They were a thing, but not so much anymore. Anyway, a description of the algorithm used to perform computation, the results of data exploration with detailed analysis, a table containing the performance metrics along with an explanation of how the metrics affects the results. So you want at least a paragraph or so that don't just throw up the performance metrics, but do some analysis of what that means and explain what it means in clear terms. Obviously include your Python source, be it a Py file, or if it's a notebook, include the notebook source. So the next question is always well, what's the data look like? So here's kind of a brief in Excel, the analytic tool of all data scientists everywhere. But it is an easy way to see what the shape of the data looks like. And so you can basically see the key thing there is that diagnosis is M for malignant. So you might want to change that to 0 or 1 depending upon how you view the diagnosis. Kind of depends probably on what you're testing for. So more detail on that data. You can go take a look at the archive, ics.uci.edu, and so on. This is a well-known data set as well. It's the Breast Cancer Wisconsin data set, and it is it's computed from some images. So you had some digitized images that they did some analysis on. They provided the characteristics of the data, and so the three-dimensional space is described in another publication if you're so inclined to look. But the basic idea is that you do have a number, probably not all that relevant for what you're doing. A diagnosis for M is malignant, B is benign, so kind of depends on which you think it should be. Probably I would, but malignant as being 1. Radius means the mean of distances from the center of the point to points on the perimeter. So it's kind of what you would think it to be, but it's kind of an average radius. Texture, standard deviation of grayscale values, perimeter area, smoothness, compactness, concavity, and so on. So lots of different measures that you would use during your classification. Taking a brief look at what some of that stuff looks like, kind of interesting, may or may not be all that useful from what you're doing, although you can see that most things have a pretty reasonable distribution, nothing terribly unusual. You either have something that's approaching normal as far as the distribution, or some of them have kind of the long tail sort of shape that you might see, and generally skewed to the right, it looks like most of the time. So that's roughly what it looks like, and you can tell by looking at that screen that I did that analysis using Kiwi. An example of what you might do as far as just exploration. A link that's relevant, that's where the data actually came from originally, the archive for it anyway. So it is there in case you want to go take a look. As always, if you have questions about what I've talked about here, if I went over something too fast, if I didn't clearly explain something, or there's some gap in what I talked about, do let me know. I'll be perfectly happy to go into greater detail in a future session, or if you want to do it through chat or email, I can try that as well. And as always, stay safe. And on Wednesday, I will probably be talking about online analytics environments, more because it's the more you know, right? So I'll be going through various environments in which you can write Python or R code, depending upon your preference. Most people these days it's Python. Could be relevant and useful for this course, especially if it's a situation where you don't have a good way of moving data from location to location, or you don't have access to a work environment someplace like at work or something, right? So anyway, it's what I'll be going over. A little bit of a survey. It's not exhaustive, but I focused on free things, so it could be relevant. So hopefully you'll be able to watch that or join. As always, stay safe, and I will speak with you on Wednesday.